In this part of the chapter, we are going to talk about phase diagrams. Phase diagrams show the pressure and temperature conditions at which a substance exists as a solid, liquid, or vapor. These regions are separated by phase boundaries: the solid vapor phase boundary, the solid liquid phase boundary, and liquid vapor phase boundary. Crossing over a phase boundary results in a phase change. For example, if our starting point, we are a solid at the shown pressure and temperature. If temperature is increased, meaning that horizontally we're moving to the right, we're going to cross the solid liquid boundary and turn into a liquid. So this is a phase change. So crossing the boundary lines result in phase change. From this point, if you decrease the pressure, meaning that we're going to go vertically down, we're going to cross the liquid vapor boundary line and turn into a vapor. There's also a point in the phase diagram that is important to note. This is known as the triple point, where the three phases meet. It is the only temperature and pressure where the three phases coexist in equilibrium. Let's focus on the phase boundaries, starting with the solid liquid line, line AB. On this line, the solid and liquid phases are in equilibrium, which corresponds to the melting point of the solid at various pressures. Crossing the line results in either melting or freezing in the opposite direction. On the curve AC, liquid and vapor phases are in equilibrium. This curve represents the boiling point of the liquid at various pressures. We have already discussed this curve when we talked about vapor pressure curves. You can see the resemblance. There's also an important point on the liquid vapor curve, point C, which is the critical point. It is the point where this curve ends. Above the corresponding temperature, the liquid phase does not exist, no matter the pressure. If the temperature is below critical temperature, compressing a gas results in condensation to a liquid, as the liquid vapor boundary is crossed. But if the temperature is above critical temperature, the boundary cannot be crossed no matter the pressure, because there is no boundary. The liquid vapor boundary line ends at the critical point. So at the temperatures above critical temperature, temperature that corresponds to the critical point, the liquid phase does not exist. Similarly, curve AD represents the conditions at which the solid and the vapor phases are in equilibrium. It also represents the vapor pressure of the solid at various temperatures. If you know the temperature, you can vertically go up, meet the line, and horizontally go to the left to read the vapor pressure of the solid. Now let's take a look at specific phase diagrams, starting with carbon dioxide. At the standard atmospheric pressure of 1 atmosphere, carbon dioxide is never a liquid. If you go horizontally, increasing the temperature, you would see that the liquid phase is never obtained because liquid phase exists above a certain pressure, not at atmospheric pressure of 1 atmosphere. This is why carbon dioxide, dry ice, sublimes directly from solid to gas. So let's answer several questions about this phase diagram. What is the sublimation point of carbon dioxide at 1 atmosphere pressure? The temperature at which the substance turns from a solid to a gas. At 1 atmosphere pressure, that transition happens at negative 78 degrees Celsius. So the sublimation point is negative 78 degrees Celsius. The next question asks the boiling point of carbon dioxide at 1 atmosphere pressure. Boiling is going from liquid to gas. However, at that pressure, liquid phase doesn't exist. Therefore, boiling point also does not exist for carbon dioxide at 1 atmosphere pressure. And if you want to find out the temperature and pressure at the triple point, you need to find the triple point on the phase diagram and look at the temperature and pressure values. For carbon dioxide, and for this particular phase diagram, those values are given. The temperature at the triple point is negative 58 degrees Celsius, and pressure is 5.1 atmospheres. The phase diagram of water is unusual because the solid-liquid boundary line is slanted to the left. This is due to hydrogen bonds that result in the abnormal expansion of water as it's cooled down below 4 degrees Celsius. One outcome of this expansion is the fact that ice is less dense than water. For most other substances, their solid state is denser than their liquid, but not for water. As a result, ice floats on water. Of course, we have observed that in our daily lives, and it seems to be the normal, but compared to other substances, this is an unusual property. One other outcome of this is observed when you walk on ice. We all know that walking on ice is hazardous as you can slip and fall easily. But is ice slippery? No, ice itself is not slippery, but when you step on ice, your weight increases the pressure on the solid, and the solid-liquid boundary is crossed, and a thin layer of liquid forms between your foot and the ice. It is that thin layer of water that makes it dangerous to walk on ice, so ice is not slippery, but water is. Now pause and answer the following questions about the given phase diagram. This question used to be a test question. Can you answer it correctly?